Our third speaker is Paul Boven from JIVE, a radio astronomy research institute located in the Netherlands, which processes the data for the European Very Long Baseline Interferometry Network. Paul holds the position of Networking Systems Engineer, and the title of his talk is White Rabbit in Radio Astronomy. Paul.
Thank you very much. Yeah, as I said, I work at JIVE. We live in a very small village, Dwingelo, in the Netherlands. And what I'm looking at today is whether we can use rabbit not just in particle physics, but also in radio astronomy. So at the bottom you see some of the hats I'll be wearing in this talk. And we'll get to them. I don't really think I need to explain White Rabbit here anymore, but just in a nutshell, you've got your switch where you can hook up to 18 devices, through an SFP, a bit of single mode fiber, another SFP, and then you go into the end node, and this is generally the end node that we are using, which is the 7 Solutions White Rabbit Zen. And using White Rabbit is like two things. You need to do a lot of calibration in front, where you measure all your delays and where you measure what your fiber is up to. And then in operation, it automatically measures the round trip time, and from this measurement of the round trip time, it determines how much it needs to compensate its own signal compared to the signal that's arriving from the master. And in this way, it keeps a very good timing accuracy. One of the projects I'm working on is the SKA project. This is a future radio telescope, absolutely transformative new instrument, huge, much larger than the current instruments, and it will consist of 2 radio telescopes, one in Australia, which we call SKA1 Low, which will consist of dipole or log periodic antennas that look straight up, and there will be 256,000 over them, spread over a distance of 65 kilometers. The other radio telescope, which is for the more higher frequency, is the SKA Mid, and what you see here is sort of a artist impression of what the dish might look like. It will be almost 200 of those with baselines up to 160 kilometers, which is the distance from one dish to the other furthest dish. And as you can imagine, this is slightly more challenging perhaps than doing White Rabbit the way it normally is done, where you have very nice and stable temperatures, maybe in underground locations where you have server rooms. What we are going to do is a little bit more challenging. As I said, distances up to 160 kilometers. The climate, semi-desert, these are very uninhabitable and fortunately also uninhabited places, which means that we don't have much radio interference to deal with. Another challenge is that in South Africa, the fiber will actually be hanging from telephone poles, completely exposed to the sun, so to say. It's still in a metal armor, but it's not nicely dug into the ground for cost reasons. It's not just going to be one type of fiber, it's going to be maybe ultra-low loss fiber, some band-insensitive fiber, so that also complicates things, and we still need to maintain an accuracy of 2 nanoseconds over that. I might be slightly more concentrating on the South African case simply because the distances are longer and the timing is needs to be a bit more accurate over there. So the first thing we went looking at is how can you extend the reach of White Rabbit, and this is certainly not original, many people have done that. You take different SFPs, bidirectional SFPs, you plug them in, and for the frequency wavelength range that you normally have in White Rabbit, you can easily extend it to 60 kilometers. If you want to go beyond that, the attenuation at 1310 nanometer becomes too big, and then we go for SFPs that run at 1490 and 5050 nanometers. From our location in the Holland, there is a nearby radio telescope which is run from there. The distance is about 35 kilometers of fiber, so we run a fiber there and back again. You have 70 kilometers. Then you regenerate the White Rabbit signal in a White Rabbit switch. You go there and back again, and then you have a 140 kilometer link, which already comes pretty close to what we need to do. As you can see here in the link performance, these are picoseconds, I hope. Yeah, picoseconds. So 2 nanoseconds is huge on this scale, and this is running the link for 2 weeks. And you can actually see the internal air conditioning of our company that doesn't do anything in the weekends, and then you see the work days, and you see the weekends again. And as you can see, it stays mostly within 100 picoseconds, so that is less than a tenth of what we need to do. Next challenge was to test this in South Africa. We're very grateful for SKA South Africa for hosting us for doing this. What you see here is the overhead fiber on the telephone poles. What you actually see here is 3 phases of power and a ground wire, and inside the ground wire is the fiber. This is the location, and we've actually tested between Clairefontaine and Carnarvon. We did not get to test at the SKA site because that's an active radio telescope, and you need to have everything that you bring there really stringently RFI tested. But the same fiber overhead is over here, which we tested on. It is the middle of nowhere, so this is one way of getting there. The other is 9 hours in a car. And then you have to bring your equipment, so you buy a really, really sturdy suitcase, you pack it with foam, and you put your white rabbits in there, and your counter, and then if you build it up, these are 2 white rabbit Zens, and a frequency counter, and here we get this fiber, which runs from there to there, and again to there to there. And then you start measuring, and you're in the middle of nowhere, you have nothing to do, you build up your equipment, you don't touch it for a week, then you go in, you make the link twice as long, and you have another week of absolutely nothing to do. What we measure here, first of all, is the outside temperature, which we get thanks to another radio telescope at the site that publishes its data on Weather Underground, so we simply scrape that. What you see here is the variation in the actual cable round trip time, which is the delay over the fiber, which all the White Rabbit fixed delays taken out. You can see the variation is in the order of tens of nanoseconds, hundreds almost. And what you see here is the actual variation between the 2 White Rabbit devices measured by a timer counter. And what you see is that it's fairly small. That is in the tens of picoseconds, maybe 50 picoseconds. For scale, the purple width is the 20 picosecond noise of the counter. And because that noise doesn't really tell us anything except that we need a better counter, we average out, and the green line is the actual data that we look at. And the first thing that you can see is that everything scales really nicely with the outside temperature, and that the compensation is fairly good. It's not perfect, it's certainly good enough. And this is on a 32 kilometer link with the normal wavelengths, and this is on a 60 kilometer link with SFPs that can do 80 kilometers by using the longer wavelengths with less attenuation. A more interesting way of looking at it is to look at it in the time domain. What you see here is the averaging time in seconds from 1 to 10 to 100, etc. And what you see here is the noise level in picoseconds, or in seconds, and so this will be picoseconds over here. So we start out with 20 picosecond noise off the counter, and up to about 100 seconds averaging time, or maybe 30. You basically only see the counter. And then if you start averaging longer, you average out the counter jitter, and you start seeing interesting effects. What you see here is basically the cycling time of the air conditioning in the server room that the equipment was in. And what you see over here is the diurnal effects, the outside temperature change, how it affects the quality of the White Rabbit link. And it's a very nice peak at exactly half of 24 hours. The interesting thing is that the green thing is the short link. Sorry, no, I've got that wrong, I think. The green is the long link, which has more noise due to the air conditioning. And the air conditioning affects the SFP temperature, which makes the SFP temperature change, which makes the SFP wavelength change, and then through the dispersion of the fiber makes the delay change in a way that White Rabbit doesn't compensate for. And if you have a longer link, that effect simply becomes stronger. The other thing is the effect over here, which is actually less on the longer link. The reason for that is the wavelengths in use are closer together. There's 2 possible effects here. It's either the change in the actual dispersion compensation and the dispersion constant of the White Rabbit link, or it can be a little bit of residual calibration error. But as you can see, this is already a 60 kilometer link, so if I do that times 3, I'm still nowhere near my actual error budget. And this is actually something I worry less about than this, and I'll explain that in the next slide. The temperature in the server room is pretty nicely controlled. The temperature of the equipment that we put in the desert, we can't put a complete air conditioning system in every dish or in every receiver. So it will be basically anywhere from, I think, 5 degrees to 45 degrees or something like that, which is a huge temperature change. If you look at an SFP and you put it in a climate chamber and you measure the wavelength, the first thing you see is a pretty darn straight line. And that's very good because all the other effects that we have are also straight lines, which is the change in the round trip time, the change in the pulse per second is actually the change in temperature times the temperature coefficient of the SFP, which is the slope of this line, times the dispersion of the fiber times the length of the fiber. And the dispersion of the fiber that we're using, standard G652.D, at 1310 it doesn't really have much dispersion, it's almost zero. And then as you go to longer wavelengths, it becomes longer. And we need to use the longer wavelengths to actually get the distance. There's a factor of half in here. The reason for that is this calculates how much the round trip time changes. If the round trip time changes by 2 nanoseconds, then the PPS output changes by 1 nanosecond because it's compensating. And the sign of it depends on whether the change was before the halfway point where the endpoint is or the other half of the link. In order to actually use this, I've written code to read out the SFP digital optical management information, which gives me the temperature of the SFP, which is very useful because over here I've put a white rabbit link, an endpoint in a climate chamber, and these are steps 30, 40, 50, 40, 30, 20, 10, 0, etc. Just going from 0 to 50 to 0 to 50 degree. And in purple you see the actual PPS output from that, which is pretty, which is changing by 500 picoseconds on only a 20 kilometers pool. So that would definitely exceed our budget if we extend that to 160 kilometer. And in green is if you just use the SFT reported temperature to compensate for it. And as you can see, the effect is almost entirely gone. What you're left with is a very little second order effect. So you can compensate for this really well, and you can just do that in software, either real time or in this case we've done this, this is with post compensation. So absolute calibration of white rabbit links is actually the difficult part here due to the dispersion. Normally, most people who experiment with white rabbit have the two endpoints next to each other. They measure the PPS and they can use the alpha parameter to get it PPS back to where it should be, and you're done. This becomes a huge issue when the other end of your link is 80 or 160 kilometers away. The reason for that is that all the SFPs that you use have a different wavelength. And that can be easily off by 10 nanometers or so. And if you take 10 nanometers, or in this case 9 nanometers in my example, you multiply it by 17 picosecond per kilometer per nanometer, you end up with an actual error on your round trip of 12 nanoseconds, which gives you a 6 nanosecond PPS error. So one possible solution is to measure for every SFP the wavelength and its temperature like I did in that graph. The other solution is to not use standard BiDi SFPs, but to use so-called DWDM SFPs. And this is also not an original idea, many people have done that. The issue is if you do this at scale, if you got 11 white rabbit switches full of DWDM SFPs, it's going to be expensive. And also the power draw of a DWDM SFP is at least a watt. So that will get you into trouble. Your switch might not be able to support all 18 links, for instance. So that is basically one option that we're still looking at, but certainly with just measuring the SFPs we can get there. And alpha on long links, well, alpha is really a bit of a fudge factor. Even if you did your original calibration not very good, you just dial in the right value of alpha and your link will be having a very low PPS error, and that looks good, but the problem is that alpha isn't actually just the ratio of the refractive indexes as it should be, but it also hides the dispersion error. The dispersion error that you get due to the wavelength of the SFP being off by a little bit. So if you then use different SFPs, you're in trouble. And you need to use different SFPs because in order to calibrate such a link, you need to swap those SFPs around. And you can't take one SFP, drive 80 kilometers, have somebody else drive 80 kilometers back, swap them around, do your alpha calibration. That doesn't work. So for that reason, we need to measure again the temperature and the wavelength of these SFPs. In the interest of time, I'm going to skip this slide. The Sagnac effect is simply as the Earth rotates, signals going one way with the rotation, arrive a bit later than signals going the other way, and that effect can still be 350 picoseconds in the SKA. Apart from the SKA, the other thing we do is VLBI, very long baseline interferometry, and what I would like to show is how we can use White Rabbit not just for timing distribution like we do in the SKA, but also do it for very long baseline interferometry. The idea is simply, we have the Westerbork telescope synthesis array over here, we have some dark fiber, we go to another location where there's another telescope. This telescope is run by volunteers, has no money, has no hydrogen maser. We can actually use this link. And to actually make this interesting and to show that we can do this over very long distance, we're going to use some public fiber from the SurfNet network and include that in the network and show that we still get enough stability to do VLBI. Penultimate slide, if that's allowed. What we need to do for this is to improve the phase noise of a White Rabbit switch. So here you have one with the low noise jitter daughter board built in, and also with a very stable oscillator built in. And that is actually not the slide. That is unfortunate. There was a different slide which I uploaded today and which was going to be here. Anyway, what you see here is... No, this is the last slide. It's just not the correct slide.
Okay.
Sorry, I was asked to replace this graph. What you see here anyway is this is a normal White Rabbit. This is what the low jitter daughter board does, and this is roughly what the addition of the very good oscillator does to your phase noise, to your island deviation actually. Thank you.
Thank you.